So here we're going to work 3 examples using Newton-Euler dynamics, and we're going to call this example series A Day at Dollywood, Dollywood, Tennessee. So the 3 examples we're going to look at are the lemon twist, the dizzy disc, and the timber tower. I don't think you'll see the timber tower at Dollywood right now, but we'll look at these 3. In each of these, we're going to use Newton-Euler dynamics to understand better motion and or forces associated with constraining components of the ride. The first one we're going to start with is the dizzy disc. Excuse me, the lemon twist. We're going to start with the lemon twist. And we'll jump here to the lemon twist and watch a little bit of action from the lemon twist. So here you go. You're on this ride, the lemon twist, and you're riding around. So we're familiar with these rides. The plate, this base is rotating at 1 speed. We've got a second rotational speed for each, in this case, these set of 3 cups. And then finally, each cup is free to rotate about its own axis. The user can either input a moment like those people seem to be doing, or they can just sit back and enjoy the ride and still spin, maybe like those kids are doing. The motion here can be described, really fully, all this motion can be described with Euler dynamics. So this is the first one we're going to look at. So let's jump over here to our model. Let's first create a model. So I've started this process. So here we have the large plate. We'll assume an axis through the center of the plate rotating with some, we can call that some alpha. Then we have the smaller discs that are located on board. That we'll call the distance out from the center of rotation out to those a capital R. We run from for the smaller plate, we have a single cup that we're interested in that has a pivot point spinning about its axis. We can call this length, let's call this length L. And then finally, there's a person here in our teacup. We'll say the center, let's assume the center mass now is at the center of this person. It's located at some distance R from its pivot. The teacup or the lemon twist is rotating with an alpha around the primary axis, a beta on the second axis, and let's just assume a theta around the third axis. We'll assume that alpha dot is constant, driven by a motor. Similarly, beta dot is some constant driven by a motor. And the theta will be our degree of freedom. And we're interested in finding equations that describe how this operator moves, how this rider moves, given these, as well as the constraints associated with the disc. So let's start by assigning frames. I'm going to assign first a inertially fixed frame here. And 1, and 2, and 3. Then I'll have a frame. My second frame I'll attach out here. I call this frame 1, so that'll be my A1, A2, A3. So first I have a rotation around the N3 axis by my alpha. Next I have a rotation around my A3 axis by some beta. That's going to be a little hard to see. I'll put this frame here. Call that my B, oh, not a B. Oops. I'll zoom in, work on that part of the drawing. I'll call this I've got an A, let's call that my C3 axis there. Here's my C1 axis. And then finally, I'm going to have a frame attached to my rider. Oh, and this frame C is moving relative to frame A with some beta. Finally, I have an axis here at my center of mass, and that's the one I'm reserving to call my body fixed frame. So that's a B1, a B3. Of course, there's a B2 over here. And that's rotating relative to C by some value theta. My Newton-Euler equations we have in front of us for this problem. I'll have 3 equations from Newton, 3 equations from Euler, but I know I'm going to need the angular velocities and accelerations to derive these. So let me first proceed to those. Move this, copy this over. Let me first proceed to those. So the first step will be to describe our motion. We can see that we're going to have rotations that relate all our frames. I'm of a rotation relating the projecting the A frame onto the N frame as a rotation around the 3 axis by alpha. So we're going to C alpha, negative sine alpha 0, sine alpha, C alpha 0, 0, 0, 1. Secondly, I have a rotation that projects the C frame back to the A frame. That's a rotation about the 3 axis by beta. Okay, just double checking. And then finally, I've got a projection of the C axis or the B axis onto the C axis, and that's a rotation around the 3 axis by theta. So I get C theta, I get S theta 0, S theta, C theta 0, 0, 0, 1. I'm going to need the the velocity and acceleration, angular velocity, angular acceleration of my body fixed frame. Let's start with the angular terms because I need that for my transport theorem. So I need the angular velocity of B with respect to N. That's going to be first an alpha dot around the A3 plus a beta dot around the C3 plus theta dot around the B3. Now this is kind of a special problem in that it's somewhat simplified. It frankly is planar in this case. We could consider a teacup where the whole plate lifts up, but in this case I didn't show that. So I need to project everything. If I choose to project everything onto the B frame, I can do that. That means I need to pre-multiply the C frame by this projection of B to C transpose. But I can see that the 3 axis preserved, and the same with A frame. So I could also get the same thing, A alpha dot plus beta dot plus theta dot in the B3 direction. Those are equivalent. By the way, this is the angular velocity of A with respect to N. This is the angular velocity of C with respect to A. This is the angular velocity of B with respect to C. Since we're here, let's go ahead and complete our angular acceleration. Our angular acceleration is going to be given as an alpha double dot plus a beta double dot, but those 2 terms are 0. We said there's a constant plus a theta double dot, so we get a theta double dot in the B3 plus the angular velocity of B to N crossed with this vector, but that's itself. So this is simply the angular acceleration. Next, I need the velocity and the acceleration of my rider. I'm going to call that located at point P. This is the center mass of the rider. Let's actually call that G. Let's call that point right there, G. So I need the velocity of point G. I get that by taking a derivative of a vector going from some fixed point on ground. I'll be back here. So that means I need a vector R first in the A1 direction plus an L in the C1 direction plus a little r in the B1 direction. Yes. I'm going to take the derivative of this guy. if I take the derivative of everybody in their own frame, r, l, and little r are all constants, so I get zeros. Then I need to take the angular velocity of a with respect to n crossed with this r, a1, plus the angular velocity of c with respect to n crossed l, c1, and finally the angular velocity of b with respect to n crossed with r, b1. I'll write these terms down. For this term, the angular velocity of a with respect to n, this is 0, 0, alpha dot crossed with r, 0, 0. This is all in the A frame. Angular velocity of c with respect to n is the combination of those two. So in the c direction, it's going to be 0, 0, alpha dot, beta dot, plus beta dot. In this case, again, everything that's in the 3 direction is common, crossed with L, 0, 0. So on the C. And then finally, I get my 0, 0, alpha dot plus beta dot plus theta dot crossed with R, 0, 0. This is in the B direction. When I cross these, I get a K cross an I is a J. So I get, and I'm going to get that in all cases. So I'm going to get an alpha dot R plus an alpha dot plus beta dot L plus an alpha dot plus beta dot plus theta dot little r. That's my velocity at G. Acceleration at G. Take the derivative of this thing first. Oh, by the way, all of these are, oops, messed up. Okay. Made an error, didn't we? Go back. We're on a roll. So first we get alpha dot R in the A2 direction. We get an alpha dot plus beta dot L in the C2 direction, plus an alpha dot plus beta dot plus theta dot R in the B2 direction. We're going to add these, now we need to combine these. To combine them, we need to project them back onto the B, we're going to put them onto the B frame. So we need to pre-multiply this guy by the projection of C onto B. I have B onto C here. So I'm going to take a transpose of that. This is a transpose of B onto C, which was cos theta. I'm taking the transpose, so the first row becomes the first column. Times 0L0. This thing's already in the B frame. I need the projection of A onto N, so I need to, excuse me, I'll get the projection of B onto A, to take the transpose of that, and multiply by alpha dot R. Got my alpha dot beta dot here. And to get that, I notice that I'll get the projection of B onto A is the product of these two matrices. I'm going to notice that when I do this multiplication, I'll get cosine beta, cosine theta, minus sine beta, sine theta. That is cosine of theta plus beta, and so on. So I will get simply the sum of these, and I have to take the transpose. So it's going to be cosine theta plus beta, negative sine theta plus beta, 0 sine theta plus beta, cos theta plus beta, 0, and then 0, 0, 1. And then finally this term. I add all these up. And so that's going to give me sine theta plus beta, alpha dot R, cosine theta plus beta alpha dot r and 0 plus sine theta alpha dot plus beta dot L cosine theta alpha dot plus beta dot L and 0. And finally 0 alpha dot plus beta dot theta dot R 0. Next, I get, and this is all in the B frame. Next, I get the acceleration at point G. And now I have to take first the derivative of this term plus the angular velocity beta n crossed with this thing. So we got a little work in front of cut out for us. The first step is to take the derivative. So take the derivative first of this guy. So we get the derivative of this thing. My alpha dot's constant, r is constant, so I just get the derivative of this guy. So that's theta dot plus beta dot alpha dot cosine theta plus beta times r. The derivative of this guy, so I get alpha dot plus beta dot times theta dot L plus 0. Derivative of the next term, I get minus theta dot. There should be getting careful with my dots. There shouldn't be a dot here. Minus theta dot plus beta dot alpha dot sine theta plus beta r plus the derivative of this guy, which is going to be minus alpha dot plus beta dot theta dot sine theta L plus my cosine theta. And then this term, so those are constants, so I get theta double dot r, and then finally 0. Plus angular velocity, which we said was alpha dot plus beta dot plus theta dot, yeah, plus 0, 0, alpha dot plus beta dot plus theta dot, crossed with this whole thing there. So see if we can write all that out. Well, actually, let's write this term once first. So we get a k cross an I, that gives us a j. So we get an alpha dot plus beta dot plus theta dot times all of this I terms. So that's sine theta plus beta alpha dot r plus sine theta alpha dot plus beta dot L. Second term we have is a k cross a j is a negative I. So we get a negative alpha dot plus beta dot plus theta dot times the j term, cos theta plus beta alpha dot r plus cos theta alpha dot plus beta dot L plus alpha dot plus beta dot plus theta dot little r. Whew. So that's that guy. Now we need to add these things up, and maybe a few things will cancel. We can keep track. I see here on cos theta alpha dot beta dot plus theta dot, so I think this thing all cancels. I'm going to be a little fast. I think all that cancels. So that's just going to be leave me with a negative alpha dot squared cosine theta plus beta r. Second term, theta dot plus alpha dot plus beta dot theta dot. Now, I think we should have that. Hold on a second. Let me double check that we didn't lose a theta dot term. Oh, yeah, we did. So we got this thing times this. So I'm going to get a negative theta dot cosine theta alpha dot beta dot theta dot. So that term cancels, but I still have a minus alpha dot plus beta dot times alpha dot plus beta dot. I guess I could just call that squared cosine theta L. And then finally, I do have this minus alpha dot plus beta dot plus theta dot squared R. Okay, second row. I get a, let's see, I've got a theta dot plus beta dot, or minus theta dot plus beta alpha dot. So we got theta dot plus beta dot alpha dot sign. So that'll all cancel. So that just gives me a alpha dot squared sine theta plus beta R. That's the first term. The next one, I get a alpha dot plus beta dot times theta dot. That cancels. So I get a alpha dot plus beta dot squared sine theta L. And then finally, I get a theta double dot R, and then 0 in the Z. Okay, good, good. There's my acceleration. Okay, so I've completed my angular velocity, my angular acceleration. Now I'm ready to write my equations. So first we'll write Newton. So I get, oh, well, first let's do what we should have done way back, which was create a free body diagram of our teacup. So we'll do it now. Here we are. Here we are on the teacup. So what do we experience? Our center of mass is here. We've got a bearing here. That bearing is going to provide forces in the 3 directions. Best free body diagram. There's going to be an FB1, an FB2, and an FB3. There's going to be a moment about B1, be a moment about B2. And in this case, we're assuming no moment around B3. So that leaves our theta as the variable. So, oh, and then of course there'll be gravity, but yeah, gravity, so it's mg just going down. This one's kind of nice, makes it simple. So first we get some forces in the x, or the 1 direction. So we get FB1 equals m times this negative theta dot squared cos theta plus beta r, cap r, minus alpha dot plus beta dot squared cosine theta L minus alpha dot plus beta dot plus theta dot squared little r. That's our first equation. Second equation, FB2 is m times alpha dot squared sine theta plus beta cap r plus alpha dot plus beta dot squared sine theta L plus theta double dot r. And the third equation, FB3 minus mg equals 0. Next, let's apply Euler's rotational equations. And we'll write them for principal axes because about the centroid. So, you know, honestly, if we assume that we just have a particle out there, then our I will be 0. If we assume that the cup had some mass, still keeping the center mass out here, then we'd have terms. Let me carry them for a moment or two. So we're going to get M1. So we get the moment about our center of mass. So that's sum of moments. So it's going to give me an MB1 plus FB3 is not going to cause a moment around 1, and FB2 is not going to cause a moment around 1. So that's all I have. So it's MB1 equals I1 alpha 1. And our alpha 1 we had 0 minus I2 minus I3, omega 2, omega 3, and omega 2 is 0. And omega 3 is non-zero, so that's just times 0. So it just tells us that the moment around 1 is 0. Then, moments around B2. So we get MB2. So in this case, we'll get FB3. So we'll get R crossed. Oh, you know what? This is about the centroid, so we would get a, no, we didn't get it, of course, there. So we're going to get a plus an R times FB3 equals I2 times alpha 2, which is 0, minus I3 minus I1 times omega 3 times omega 1, which is 0. And then finally, MB3, which we don't have any. Do we have a moment around the 3-axis? We do. We get an FB2R that's negative. And I'm doing these moments by inspection caused by the perismatic force is I3 alpha 3. So that's non-zero. Let's put in the value for alpha 3. That is theta double dot. Minus I1 minus I2, omega 1, omega 2, that's 0. So here are my 3 equations. Notice my equations. Okay, so now I've got my, here's my 6 equations. I'm going to highlight my unknowns with this marker. My constraints are unknowns. There's 1, 2, and 3, 4, and 5. My remaining unknown is here in theta double dot. And I had these again, but I'm not going to necessarily need to count them again. Here's my theta double dot. To solve this problem, to proceed to the next step of solving, you know, it's really a what we call here a set of differential algebraic equations, technically because I've got constraints and equations of motion tucked inside. To solve, I'll write them as matrix equations. So I'll have my I'll write down my unknowns: FB1, FB2, FB3, MB1, MB2, and theta double dot. I don't think I allowed myself to room there, did I? So we can do equals my right-hand side. So first equation, FB1. So we get FB1 times 1. There's no FB2, no FB3, no MB1, no MB2, and no theta double dot. And so that just equals all the stuff on the side. So M times negative alpha dot squared cosine theta plus beta R minus all that stuff. Second equation, I get an FB2 and I get a theta double dot R. So I get 0, 1, 0, 0, 0, negative R equals all the stuff that was then on the right side. M times alpha dot squared sine theta plus beta R plus stuff. And the third equation, FB3 equals MG. Fourth equation, MB1 equals 0. Fifth equation, MB2 equals R FB3. So I get an R there, a 1 here, and a 0 on this side of the equation. And my last equation, I get a negative R FB2. I get an I3 FB3. And oops, it's going to be negative because I've got to pull it over. And then I end up with a 0. So here are my equations. If I call that my coefficient matrix C, I'm going to solve for these unknowns as the inverse of C times this vector here. The first 5 of these will solve for the constraints. The last one will give me an equation for my theta double dot. Yeah, gives me an equation for my theta double dot that I can then integrate in time.